everyone, welcome back to alkaline hydroxide 784, and today in the chemistry series we'll be looking at hydroxy compounds in organic chemistry for that matter, and this is topic 11.5. Okay, so as usual we'll be going through the learning outcomes, and that's pretty much what we'll be doing. So the first learning outcome is about the chemistry of alcohols, and exemplified by ethanol. So hydroxy compound just means something with a OH group. So that would include, if you're looking at alkanes and alkenes, it will be alcohol. Or if it's something that is aromatic, then it will be something like phenol. Yeah, so that's pretty much what you're going to look at. So for the first learning outcome, you can see what happens, what kind of stuff you can do with the alcohols basically. So the first thing is combustion. Well, like with any organic compound, you can pretty much just burn it. Okay, maybe not any compound, but a lot of them you can kind of burn technically. So if you provide enough oxygen and you burn the so-called like the alcohol, you eventually get carbon dioxide and water vapor. Yeah, that's the formula. If like the formula that I'll provide here is based on something that only has one hydroxy group and not more than one, so it's not like a diol or something. It's only one ol in the sense. Okay, so yeah, it's pretty simple. Just provide enough heat and enough oxygen and it becomes carbon dioxide and water vapor. So the next reaction that it can undergo is nucleophilic substitution. So in nucleophilic substitution, you know that we're going to substitute the OH group for something else. So in this scenario, the thing that we're going to look at is halogenoalkane. So you're going to substitute the OH group to give you a chlorine, bromine, or whatever that is. And once again, all the conditions will be written on the paper because I don't want to accidentally say something wrongly and then, mess up. So I'll just give the actual conditions in the paper so it's easier for me to move quickly. Okay, so the next, so this one is really just to replace the OH minus with the Cl. So the next reaction would be the reaction with sodium. So sodium is, an alkali metal in a sense, like in the first group. So when you put it in water, it kind of, makes some noise and it's like if you put a small little piece, it'll start dancing around the water and you get a lot of hydrogen gas from that reaction, right? So the same kind of thing happens when you put sodium into alcohols, especially, like since alcohols are also kind of like water in a way, they're polar compounds and they have this wonderful little OH group for the sodium to react with. So what happens is that the sodium reacts with the OH minus and it becomes NaOH. And I guess you probably don't need any real conditions for this. You just need to put a piece of sodium into ethanol and you will get NaOH, and the resulting in like the the ethyl group will then how do I put this? Actually, it's not really NaOH. It's more of like Na with the ethanoic ion in the sense. That's more of a salt. Because when you react it with water, it's like one of the hydrogens goes away, so it becomes NaOH. But when you react it with ethanol, it only has one hydrogen per se, so it's more of like the ethanoic anion and the hydrogen plus. So the hydrogen plus will become H2 and ethanoate will join the sodium, so it becomes a salt. Okay, so the next reaction would be the oxidation to carbonyl compounds and carboxylic acids. So yeah, we saw this last, I don't know when we saw it earlier. So if you, instead of trying to burn it, you try to oxidize it instead. You use your manganese ions and your sulfuric acid and you can get carbonyl compounds or carboxylic acid. So if you want to not make it too oxidized, you can try using instead of manganese, you use chromium. Wait, what? Like the chromate ions, like K2Cr2O7. I think I said that wrongly. But yeah, basically that you use that and you immediately reflux it during, like, if you reflux and immediately distill it out of the reaction. That's what you do in order to prevent full oxidation. But if you continue to oxidize it, you will get a carboxylic acid. Yeah, so that's how this works. And yeah, for both of them is really heat under reflux. So if you want to get a carbonyl compound, you have to immediately distill it out. If you want a carboxylic acid, you either just use KMNO4 or you reflux it for longer and don't distill it out. Yeah, that's how you do it. K2Cr2O7. Yeah, actually that's correct. Okay, cool. So the next one is dehydration to alkenes. So basically you can kind of remove the OH plus another H and you can dehydrate it back to an alkene. So I'll write the conditions for that in the equation as well. Okay, so the next learning outcome is to suggest characteristic distinguishing reactions for the different classes of alcohols. And basically what they mean, the primary, secondary, and tertiary ones. How do you distinguish between the three different substitutions of alcohols in a sense? So in a primary alcohol, you have like two H's on the same C. In a secondary one, you only have one, and in a tertiary one, all of the three are like, not H basically. All the R groups will be there. So if you do mild oxidation, if you think about it, whether you do mild or strong oxidation, if you have a primary alcohol and you only mildly oxidize it, it becomes um it becomes a aldehyde. And if it's not a primary alcohol and you instead more of like a tertiary one, or a secondary one might also be the case. Even secondary one, you would get a ketone. So in that scenario, you can kind of identify the two different kinds of carbonyl compounds that you can get. And if it's something that you strongly oxidize, when you have a tertiary alcohol, you can't really get a carboxylic acid. But when you have a primary alcohol, you can definitely get a carboxylic acid out of it. So basically you use reactions like that to figure out what's the difference between, like, how substituted it is in a sense. And and yes, there's also another thing that you can use, which is actually in the next learning outcome, the reaction which involves creating triiodomethane. So what this requires is you have a group which is CH3CHOH. So what this means is, like, the thing is not a primary alcohol but more of a secondary one, because there's still one H on it, and this will react with alkaline aqueous iodine. So if you put iodine in aqueous solution, usually I think ammonia, then you will get triiodomethane when you react it with this. So triiodomethane is just CHI3, so that is triiodomethane, and it appears as a yellowish oily liquid or something like that. So that's how you can try to identify a certain kind of substituted alcohol, because this is more of a secondary one. It's not primary, it's not tertiary, but it's in between. Okay, so the next learning outcome would be to recall the chemistry of phenol as exemplified by the following reactions. Oh wait, before that, you might be wondering whether this particular test will work with other variations of the group, right? Like the oxidated, the ketone version might work because it's pretty much the same thing just without the H in it. So that will actually kind of work with the triiodomethane as well. So but the easiest one to look at is basically just the basic form of the Tesla, the CH3CHOH. Yeah, so that's pretty much it. And if there's already like iodine or something on it, it will still work. On the CH3, if there's like CH2I or something, it still will work. Yeah, that's the side note. Okay, so if we go back to that next learning outcome, we look at the chemistry of phenol this time, which is the OH group attached to a benzene. So phenol can react with bases, with sodium, and it can be nitrated or brominated. Okay, so if you react phenol with a base, phenol will act like an acid. It will be like a phenoxide ion, and the H will then join the base, I guess, kind of. So let's say maybe you're reacting it with something like I don't know. Okay, let's just call it like a base BOH. That's what the base will be called. So the phenol plus the BOH will give you B and the phenoxide ion together plus water. So of course the whether they're actually together kind of depends on whether it's aqueous solution or not aqueous. Is it not really aqueous solution, but is it in solution or is it like a solid that that is big enough to like precipitate out or something like that. So yeah, it kind of depends on the context. So that's how it would react with a base. So with sodium, basically you would expect it to give you sodium phenoxide and H2. Yeah, so that's for sodium. And the last one is nitration or bromination. So this is not with regards to the phenol group itself, but with regards to the benzene ring. So you can nitrate the benzene ring or you can brominate the benzene ring. But the thing is, since there is a phenol and the OH group is, well, if you go to your what's that thing called, the data booklet, sorry, you go to your data booklet, then we know that the OH group activates the benzene ring. So what does that mean? Well, it is electron donating. So wait, yeah, it's electron donating like an alkyl group, and it activates the benzene ring. So the benzene ring is more electron rich. It's more nucleophilic in a sense. So if you're trying to nitrate it, what happens is the like for nitration you would need it to be more of an electrophilic substitution, right? So yeah, so it should work a little bit better with the OH group on it. So I'll just write the actual like the conditions and compare it to what it would normally be, which I think is 55 degrees, the normal conditions, right? Okay, so I suppose with activating group, you would have it maybe at room temperature or 30 degrees around there. Okay, so the next one is bromination. So for bromination, it's the same logic. I think if you are doing UV, then there's nothing much to really say. But if you're doing bromination in sense of the wait, is it the AlCO3 one? Yeah, basically something like that, then the conditions might be different compared to the usual conditions. And that's because the benzene ring will be more nucleophilic, and therefore electrophilic substitution will be a little bit easier in the sense. Okay, so the final one is about the relative acidities of water, phenol, and ethanol in aqueous medium. So you're going to look at them as Bronsted-Lowry acids, which means that the way to explain this would be if the if the conjugate base is more stable, then we can say that the particular thing is more acidic. So by the conjugate base for water, it would probably be OH minus. For phenol, it would be the phenoxide ion, and for ethanol, it would be the ethanoate ion. I'm not sure if I'm saying that correctly, but anyways, you get the point without the H basically. So which one is more stable? Out of the three, the phenoxide ion will be the most stable because you have the benzene ring there, and we even have like an activating OH group on. I mean, the OH group is the main thing, but you get the idea. There's like an O with a wonderful p orbital that can share electrons with the rest of the benzene, and it's just really nice and stable on its own. So you can kind of explain that with the delocalization of electrons about the benzene ring, as well as with the the p orbital in the O. Yeah, so that should be simple enough to explain. Just use your delocalization to explain that. And then for the next one will be ethanol. The ethanoate ion is somewhat stable, but not as stable as the benzene ring because the ethyl group is electron donating, so it will give more electrons to the O. Yeah, so likewise the idea is that the O is somewhat somewhat more negative. Okay, I don't really know what I'm saying. Okay, anyway, so the ethyl group is electron donating, so the O can keep all the electrons in the sense. And for water, the thing about water, it only has OH minus and O just has a H with it, and two pairs of lone electrons and stuff. So in that scenario, I guess it's not really the most stable ion on its own. And also because since water isn't technically acidic or basic in a way, like if you think about it, like the idea of acidic and basic in this scenario would be what happens when they react with water itself. So if you think about it, water react with water gives you H3O plus and OH minus. Kind of sounds a bit funny. So yeah. I mean it happens, but at the same time it's not very stable. It's likely to revert back just as quickly as it happens. Like it just keeps happening and reverting back, I guess. I'm not exactly sure what happens in reality, but the point is the overall pH is still gonna be 7. So yeah, so technically water is the least acidic, then ethanol is slightly more acidic, and then phenol is more acidic than ethanol. But of course, don't really expect them to be particularly acidic. They're probably not really the most acidic things there are because they are not strong acids. They are weakly acidic. So yeah, don't expect too much from them. But in aqueous medium, this is their relative acidity. So if you are during the exam and you're confused, all of a sudden you kind of forgot, oh no, which is more acidic or which is more basic. How do you try to help yourself remember that? Well, what you can do is you can kind of go to, what can I say? Okay, so if you go to page 53, there is this table here. I'm pretty sure it's meant for something else. So I don't advise you to refer to this table or something. But the thing about this table is that there is, alcohol, phenol, carboxylic acid. So if you go here, you then realize that, it seems to be as you go down that particular bunch of like these three, you can see that the number increases. So for alcohol it's like 0.5 to 6, and then phenol is like 4.5 to 7, and carboxylic acid is 9 to 13. So this means that the acidity kind of increases as the number increases. Is that correct? Might be asking. If you look at the amine it's supposed to be basics. The number appears to be higher than the alcohol, so I wait, no, it's amine basic, not necessarily. I don't know. But anyways, I mean, if for these three, maybe you can use this particular comparison. It's just like just in case you suddenly forget, then you can just go and quickly check this and see, oh, okay, it's in this order. Cool, great. Yeah, then you can just go and answer the question using the explanation that you remember. But anyway, that was please don't depend on that table though. So you only use it as a memorization trick or something. Because I don't really get the table either. It's about some chemical shift in the protons. So yeah, I think it's meant for H3, not meant for this. Yeah, that's pretty much it. Okay, so I hope you find this video useful. If you did, please press the like button and subscribe. And with that, I would like to say thank you and bye.